This is Physics 1 course. In this video, I will solve another example on constant acceleration motion. The velocity time graph for a particle is shown below. So this is the velocity, meter per second, and this is time in seconds. Find the acceleration at time equals 2 seconds at this time. Find the location of the particle at time 2 seconds with respect to its location at time 0 seconds. So location at this time with respect to location at this time. Notice that there are three lines. One is Vx, it's the red. One is Vy, it's the green. And Vz is the blue. These are the three components of a velocity vector v. Let's now find the acceleration. So we know that acceleration is a equals dv divided by dt. It's equal to the limit delta v vector divided by delta t when delta t goes to 0. This means that ax equals delta vx delta t, and ay equals delta vy delta t, and the same for az delta vz delta t. Now remember, if I had this triangle and this was delta v, some number 3, 4 something, and this was delta t and this was theta, then tangent of theta equals delta v over delta t. So it's the same here. This edge is delta v, this edge is delta t, and therefore the angle is theta and the tangent is simply a. So this is a. Therefore, for a constant slope, that means acceleration is constant. On the other hand, when acceleration is constant, the average acceleration is equal to the instantaneous acceleration. Instantaneous acceleration means delta t goes to 0. Average means delta t can be large. Now I'm going to derive ax. So for ax, I have two slopes. Therefore, ax has two values, two different values. One slope is here and the other is here. So for time less than 1 second or equal to 1 second, this is the acceleration. For time larger than 1 second, at least up to 2 seconds, it has another. So let's work on the first. Here delta v is let's say delta t is 1 minus 0 and delta v is 1 minus 0. So therefore it is 1 meters per second square. For the other one, I have delta t is 2 minus 1, but the delta v is 1 because it's 1 minus 1 minus 1. Therefore it is 0. So now for ay, it's all the way the same slope. Therefore ay is the same for the whole period, and it is 0 because at time 2 minus 0, at time 2 it was 0 and also it remains 0, so therefore it's 0. For az, again we have two different slopes, therefore there are two values for az. Again, for time between 0 to 1, the slope is the same. For time 1 to 2, the slope is the same. So the same interval is here t less than or equal 1 seconds, t larger than 1 seconds. And now the second part, the slope is 0, right? The angle is 0, so therefore it's already 0, similar to here. For the top, delta t is 1 minus 0, 1 minus 0, like here, but here delta v is 2 minus 0, so it's 2 minus 0, so therefore it's 2 meters per second square. Now let's go to the second part of the question. Find the location with respect to the location at 0. So it basically is asking for location vector at time t equal to, which is when particle is here, minus r naught. We already know r is x I hat plus y j hat plus z k hat. So this is the r. So therefore this is x at time t2 minus x naught I hat plus y at time t2 minus y naught. Let's put them in parentheses. J hat plus z at time t2 minus z naught k hat. So I will derive this component, then the rest is very similar. You can derive it yourself. So remember I had x minus x naught equals v x naught t plus half ax t square. Also remember that I said this equation is only valid if ax is always constant. So now look at here, ax is not always constant. It is constant for this period, it is constant for the other period, but not always constant. So what we can do, we can break the problem into this interval and solve, then break it into the other interval and solve to find the final answer. So let's say for the first interval I have x at time t equal 1 seconds, so let's say 1 seconds minus x naught equals vx naught at time t equals 0, vx is 0, so therefore it's 0 already, plus half ax, which is 1 meters per second square, time, which is again 1 seconds, because I'm going to find it at 1 seconds, 1 seconds square. So basically this second square and this cancel out, it gives me 0.5 meters or half meters. Now let's solve the problem for the second interval where ax is 0. So here x at time t equals 2 seconds, and this acceleration is only for time between 1 second and 2 seconds. So therefore I can't go beyond 1 second. So let's say my x naught here is, the naught now refers to t equals 1 seconds. So I basically want this. So it equals to vx naught now means vx at time t equals 1 seconds. T minus t naught plus ax half t minus t naught square. So ax is 0, this term is totally 0, and vx at time t equal 1 is 1. So it is 1, then t is 2 seconds minus 1 seconds, so therefore it's times 1. The unit is meters, so it is 1 meters. Now x t equals 2 seconds minus x t equals 0 equals x t equals 2 seconds minus x t equals 1 seconds plus x t equals 1 seconds minus x t equals 0 seconds. So now I have this thing equal to, I derived it here. Yes, it's 0.5. This thing is 0.5. And this is 1 meters. So 1 meters plus 5.5 equals 1.5 meters. For y and z it's the same. I just write down the equations. So basically you want to use y minus y naught equals v y naught t minus t naught plus half a y t minus t naught square. So remember, usually t naught, this naught refers to t naught equal to 0. T naught equal to 0. That's usually the convention. That's why we usually write vy t plus half ay t square, because t naught is usually 0. But in this particular example, t naught could not be taken 0 in the second part. So the same thing is for vy. So vy minus vy naught equals a y t minus t naught, and also the same set of equations is for z. Z minus z naught equals vz naught t minus t naught plus half a z t minus t naught square, and vz minus vz naught equals a z t minus t naught. So these are the set of equations that you need to use to find r minus r at time t equals 0, or at time t equals 2 seconds. Thanks for watching. Please subscribe to support my channel. If you have any question or comment, please send me an email at open.physics.project@gmail.com. Thank you.